much, everyone. This is the savannah of a monolithic application architecture. Not too many features, relatively easy to see the major landmarks, and you can also see danger coming from a long way away. But this is the jungle of microservices, where danger lurks behind every rock, tree, crevice, and service interface. And I'm here today to talk about a particular type of peril. The one that I'm going to talk about is the peril of partial failure. So we should probably start by understanding what partial failure is. If this is something that's particularly dangerous to us, it'd be nice to know what it is. So let's start with our monolithic application. And many applications are structured in the following way. We have a module that encapsulates some functionality, and we have another piece of the application that wants to take advantage of the functionality. And this is something that we learn in initial programming classes, where I make a call and I expect to get a response. Now, let's move to a service-oriented sort of scenario where I've taken that functionality and I put it in its own service. Now, I still expect to make a call and to get some kind of return value from it, with the exception that I'm now crossing a process boundary. Okay, so what I've done is I've taken a local procedure call and I've turned it into a remote procedure call. Okay, so this is really where the source of this partial failure comes from. So anybody familiar with this paper? It's called A Note to Undistributed Computing. It's actually kind of an unassuming paper title. It was published in 1994 by some folks from Sun. And what they were looking at, and what the research community, the distributed systems research community was looking at the time, was kind of a magic bullet. They wanted to take a program that had been written to run on a single computer, and they wanted to magically take pieces of that program and have them run on other computers using sort of runtime system and compiler support. And the idea was that the original programmer would not have to be involved in this, right? I could write my program as if it was going to run on a single computer, and then magic would happen and suddenly it would be a distributed program. Now, in this paper, they examine some of the challenges here, and the main thing that they come away with is that it kind of doesn't work, that as soon as we have pulled things into distributed systems, something has fundamentally changed. Now, in the paper, they identify 4 sort of major challenges. Some of them, are not quite as applicable to a microservices setting because we actually, can enlist the help of programmers who understand that they're building services, right? So some of the problems are, hey, can we do this automatically? And when we actually have programmers help, those are not problems anymore. But the one thing that they identified, as it turns out, and I really like this slide here too. So they discuss what's necessary if you're going to take distribution seriously, which is kind of academic trash talk for like everybody up to this point has not been serious about this topic. So as I mentioned, the key challenge is this idea of partial failure. So this is the idea that in my distributed system, I can have parts of the system fail while other parts of the system continue operating. This is actually a desirable quality in many cases, right? This has good availability effects in some cases, right? That just because this service went down doesn't take the entire application down with it. But there are some challenges that come into play. And so let's talk about this. So we have a remote procedure call setting. So I have a client and a server. And as it turns out, there are a number of things that can go wrong. So I could send a request to the server, but the network could drop it. Or I could send a request to the server, and the server's crashed. Or I could send a request to the server could generate a response, but the response is dropped by the network. Or I could send a request to the server could start working on processing it, but it takes a long time, and I give up. And so I time out, and I don't see a response even though it might be coming later. Similarly, I could be sending a request. The server could generate a response actually quickly, but the network might be slow to return the response. And I might also get tired of waiting for it. And now here's the tricky thing. Okay, so in all of these scenarios, the interesting thing is that in some of these scenarios, the server has processed the request, and in some of them, they haven't. But these scenarios look identical to the client. And this is the fundamental semantic ambiguity that comes into play once you can have this partial failure. Something didn't come back. What actually happened to it? And so it turned out this was not something you could automatically recover from. Now, as it happens, I have something backstage that I think will really bring this home to you. So if you just excuse me, I'll go grab this real quick. How long are you willing to wait for me to come back? So this is the challenge that we face, and really what it boils down to is that once we start making remote procedure calls, these are a lot less reliable than local procedure calls. And so if we don't take that into account, we're going to run into problems because we're making an assumption that something is reliable when maybe it isn't. Now you may be saying to me, no, well wait a minute, hold on, this doesn't apply to me, right? And I'm going to say, no, you are in a state of denial. So one source of denial is, Vint Cerf, he's a pretty smart guy, and I use TCP, right? So TCP is reliable. But how many people have experienced the TCP socket timeout? Right? Did your data get sent? It didn't, right? So TCP isn't a magic bullet. It's not magical. So TCP isn't perfectly reliable. But then you may say, well, you know what? All my services talk to each other over LANs, and everybody knows that you don't ever see network outages on a LAN or partitions between segments of a LAN. Well, as it turns out, you do. This is a great survey paper that was published by Peter Bayless and Kyle Kingsbury, where they actually surveyed a bunch of documented outages from around the industry, and really what they found is that communication failures happen sort of all over the place, whether it's across a wide area network, across LANs, all different types of networking technologies. So these sorts of events really do happen. The final objection is, I say, well, John, you're talking about remote procedure calls, and we all know in an API setting that's SOAP, right? And so, well, I don't do SOAP, right? I don't do that. I do REST, right? Maybe hypermedia APIs, right? Something like that. But I would say, well, hey, if your APIs are being accessed over HTTP, no, you are still doing remote procedure calls. And let's take a look at this. Here's a GET request. I would argue that this is just a remote procedure call that has a certain signature, right? I'm reading some data from some path. Puts are writes, right? So I'm writing some data to a particular path. Now you may say, well, wait, hey, I got you. You didn't return anything here. But just the fact that it does return is actually still something that's coming back, right? So even in this case, even if no data comes back, I get an HTTP response. Similarly, if I have posts, this is some sort of generic application function. And so the reality is if we're using HTTP-based protocols and APIs, these are still request and response protocols, and these are still remote procedure calls, and so we're still subject to the danger of partial failures. So, as we take our application, we divide it into multiple services. Essentially, we're introducing all of these cracks in our overall application where partial failure can creep in. And so, I found actually yesterday, I found a great tweet about this. So Neil Conway is a distributed systems researcher, and he said, Microservices, because solving business problems is hard, but building loosely coupled, fault-tolerant distributed systems is easy. Obviously, this is tongue-in-cheek. Companies wouldn't be pursuing microservices architectures if they didn't see holistic overall business value. But I think the point to be made here is that there is no free lunch. And so I guess for the rest of the talk, I'm going to talk about what lunch is going to cost you, and then also how to maybe get lunch as cheaply as possible. So partial failure is going to happen, and so we're just going to have to deal with it. Some things that we found effective at Comcast, and we've had a heavily services-oriented architecture for years now. we have found three sort of major strategies to be really effective with dealing with this. So the first one is the idea of idempotence. So an idempotent operation is one where after I've applied it once, I can apply it as many additional times as I want afterwards, and I still get the same result. So an example might be multiply by 0. Right? I multiply by 0, and then I multiply by 0 again, and again, and again, and I still end up with 0. Right? So that is an idempotent operation. Idempotent operations are great because they means that you can retry them, and you will end up with the same result. So this is a nice way of addressing this semantic ambiguity, right? Which is that, hey, I didn't hear back from my operation. What do I do? Like, did it work or didn't it? Because we saw all those scenarios where sometimes it worked and sometimes it didn't. I can just try again, and I know I'm going to get the same result. And so there's a lot of power to be had here. A really common example of idempotent operations is the concept of set points. Right? So thermostats are kind of a good example. So the interface to a thermostat basically lets you set a target temperature. Thermostats don't ordinarily have an interface where you can say, please make it 2 degrees warmer right now. Because as we know, it can take a while to heat up a room. And depending on the number of people that come or go from the room, we may not end up where we wanted to. And if I get tired of waiting and I go back and I say, please make it 2 degrees warmer, what should the heating system do? Right? Have I gotten tired and this is a redundant instruction, or did I really want it to be 4 degrees warmer than where it was when I started? So the idea of this target set point is a really robust sort of control loop concept. A place that we apply this is at Comcast is on, we have a mobile app, and one of the things that you can do is you can schedule a DVR recording for a show. This is something that's really important. If somebody says they would like to record the new Game of Thrones episode and you don't record it, that's a big problem. So we're able to take advantage of this by designing an idempotent interface. So if the mobile app attempts to make the recording, all that's really doing is trying to set a please record this bit on a record somewhere. And whether that takes a long time or there's a network problem in the middle, it's okay because I can just retry that and then look at my set of scheduled recordings until I see that it's scheduled to be recorded. Right? So this gives a really robust way of generating a control loop for this application. Now, one of the things that we noted here is that and an interesting pattern that we found was because this is happening over a wide area network, this sort of the time it takes to go around this loop can be can take quite a while and obviously consume the subscriber's network data rates on their plan, and so we're able to actually run sort of nested control loops here where we can sort of take longer cycle turns around, hit something inside the data center that can also do the retries, right? So we're able to sort of cascade that and provide something that's a little better. Idempotence is also interesting because the example that I showed above is not quite so simple, right? Our DVR service actually runs in multiple data centers for redundancy reasons. And so one of the things that might happen is, my mobile application might say, hey, please record that show. And so the DVR service will say, okay, I will record that show. But there might be a network partition between the data centers. And so when that instance of the service tries to replicate the fact that I would like to record that show over, we can't do the replication because it can't actually talk to the other side. Now, during failures like this, it wouldn't necessarily be out of line for the next time for the mobile application to come and sort of say, hey, is that being recorded over here? And this DVR service will say, no, you haven't asked me to record anything. So I'll say, well, no, I really want it to be recorded. So now I've done sort of a write on either side of this partition. At some point later, the partition is going to heal. And I'm going to want to reconcile the service state across the data centers. And the fact that this operation is idempotent is really convenient because it means that the state on both sides ended up at the same place. And so it didn't matter whether I wrote it on one side and then replicated it over, or I did the writes multiple times on either side, that they're ending up at the same state. And so it's easier to understand how to reconcile things on the service state at the backside. So that's sort of the first concept, is that if we can design idempotent service interfaces, this is really a nice way of recovering from these sort of partial failures. Again, in the context of HTTP, the put method is actually defined to be idempotent. And in particular, it's visible to intermediaries. And so because put is defined to be idempotent, it means that an intermediary that sees you're trying to do a put request can actually retry it on your behalf without necessarily even understanding anything more about what you're trying to do. And so this pattern that I showed here, where maybe I had an application-specific proxy, if I'm using HTTP with put, this can be a generic HTTP proxy, right? That I could actually use this for multiple services with idempotent interfaces, because the put method is just something that, hey, that's a put method, so I can retry that. So we're able to make this pattern a little more general. Now, it's not always possible to design idempotent interfaces. And so sometimes you just kind of have to let the jungle win. So in this case, we're going to try to just deal with the fact that we had a partial failure. I see that I had a partial failure. What am I going to do about it? Success in this case really relies on drawing your service boundaries in the right place. And so what I want to do in the next section is to talk a little bit about ways to think about drawing those boundaries in sort of healthy ways. So, because this is what lets you do graceful degradation for your overall application, right? So the idea is that things may be looking like this in your data center, but from the point of view of your consumers, they're still sort of floating gracefully above all of the chaos. So this is what we're shooting for, and there's a few patterns that can be useful for doing this. So the first one is to think about dividing functionality between things that are synchronous to the client and things that can be asynchronous from the client's perspective. So a good example of this is if I have a client that would like to watch a movie, the synchronous part of that is show me the movie. But an asynchronous part of this might be, hey, remember that John asked to watch that movie so that we can recommend other movies that are similar to it at some point in the future, right? So that's something that could happen later. So in particular, as long as I have a way to remember that I watched the movie, I don't actually have to update the recommendation system right then. And so what that means is that the availability from the point of view of the client isn't tied to the availability of the asynchronous processing part, right? So this gives you a way to sort of recover from the partial failure by just trying to do it later, right? And masking the rest of it from the client's perspective. The other way of looking at things is to distinguish critical functionality from not so critical functionality. So for example, when you go to Twitter's homepage, right, there's a nice while you are away module that's up there, right? If that's its own service and that happens to have an outage, well, that's okay, I just don't show that, right? Because the key thing is I can still show you your main Twitter timeline and recover from it. So it's not sort of the full functionality we would like, but I've still gotten the critical pieces of it there. And so again, this is a case where if I encountered a partial failure to an optional piece of functionality, I can just ignore it and sort of move on from it. Another strategy is to provide alternative implementations. So as I mentioned recommendations before. So if you go to the Xfinity TV website, we ordinarily like to show you personalized recommendations for things you might like to watch. Well, if there's an outage in the recommendation system, something simpler we can provide is, well, here's a list of our editor's top 20 picks, or here's the top 20 things that people are watching right now, which that's relatively easy to, it's not a lot of data, it's easy to sort of keep it relatively fresh. And so again, even though it's not the full functionality I want, I can give you something else instead that's at least better than nothing. And then, the last piece that I think is really important is the concept of caching. And this is something where the use of HTTP-based APIs, I think, have a really big advantage, because HTTP as a protocol has a really rich set of caching semantics that it can express. And in my experience, most people are actually aren't even aware of sort of the full richness of expressivity that can be expressed there. So I'm not going to this is not going to be a full HTTP caching sort of exercise, but I do want to touch on a couple of things that are related to partial failures. So one of the things that the HTTP protocol specification explicitly allows a cache to do is if a client makes a request, obviously if a cache has a fresh cache entry, right? So cache entries have a lifetime, right? It's like you can hold on to this copy for, say, an hour, right? This is good for the next hour. So at some point, though, it's later than an hour. So now my cache entry is stale. At that point, the cache is supposed to check with the origin, hey, is this cache entry that I have still good? Can I still serve this? Now, if I encounter a network error at this point, the cache is actually allowed to just serve me the cache entry even though it's stale, but it's required to actually tell me that it's stale. So there's a specific warning header that it sets that says, hey, the cache is stale. An interesting thing is that if I happen to see that warning header, as a client, I may say, hey, you know what? That probably means the origin server wasn't happy at that point. And so one of the things that I can do is, as a client, I can actually change some of my expectations about freshness. So one of the things I'm allowed to do is to say, hey, you know what? If you have a cache entry, as long as it's not more stale than this, I'll take it, even if it's sort of, technically stale. And so in this case, again, the cache can actually give me that stale cache entry, but without having to try talking to the server. And this is useful because usually it only knows that it can't actually talk to the server due to a timeout of some sort. So this allows me to avoid waiting for that timeout to happen before I get my stale cache entry. And so this allows the client and the cache to sort of participate together in sort of a circuit breaker style approach. And this is all built into the base HTTP protocol. And so that's a really useful thing to look at. And here's the warning header that it's going to give me, which literally says this response is stale. So here's one that is actually an extension to the sort of core caching semantics. So it's documented in RFC 5861. And so we'll see how this works. So we're going to start from sort of an empty state here, where a client's going to make a request for some data. It's going to hit the cache. The cache says, this is new to me. I don't have any entries, so let me go ask the server for it. Now, on its response, the server can actually mark a directive that says stale if error. And so how many people have seen this cache directive before? Okay, so this is new to most people. So this is useful. So we'll see what this means in a minute. But so then the cache stores the cache entry, and then it returns the response back to the client. So then we'll wait a little bit of time. And in fact, we'll wait long enough that the cache entry has become stale at this point. Okay, so I go to make a request. The cache says, aha, I have a cache entry, but it's kind of too old. So I'm supposed to validate this with the origin to see if I still have the up-to-date data. And so it'll send the GET request. And it may have a validation header on it, like if none match. This is a way of saying, like, do I have the most up-to-date piece of data here? Now, one of the things that might happen is that I may get an error from the server, right? So a 503 error is temporarily unavailable. And so this is common if an application server happens to be temporarily overloaded. It actually just says, don't talk to me right now, I'm busy, okay? By default, and by the sort of normal processing of HTTP requests, I would have to forward that 503 error to the client and invalidate my cache entry. However, I had that stale if error directive. And so what that explicitly says to the cache is, no, actually, you got a sort of temporary error that doesn't sort of strictly invalidate the cache entry. You're actually allowed to serve the stale cache entry, and that's correct. And so the combination of these two sort of mechanisms that we saw, one where there was a sort of an implicit error, right, with the network timeout, and another one where there was an explicit error like this. These are two different sorts of partial failure conditions that HTTP lets us recover from, right? So, and these are in cases where sort of stale data is better than no data. Obviously, that's not true for every sort of possible interaction. Sometimes you really need it to be up to date, but you'd be surprised at how often the stale stuff works out in practice. So the canonical example, right, of strongly consistent application semantics is the bank account. Right? It's like I'm not allowed to overdraw the bank account. Banks do not actually work this way, right? If an ATM machine is disconnected from the network, it will still give you cash. But if you didn't have enough money in your account, your bank will come and make a compensating transaction afterwards, right? It's actually not nearly as strongly consistent as we might think. And so there's actually plenty of places where this sort of level of strong consistency isn't actually required in practice. So the final strategy that has been really useful is to really just simplify things. And so I'll give an example. So if the problem is that I have all of these services to the point where I have a jungle, right, where I have all this partial failure coming at me, well, how do you simplify a jungle? Well, you simplify a jungle with a machete. And really this is sort of an admission that I may have actually chopped my application a little too finely. I certainly have gotten really enthusiastic about technology or a methodology or some other approach, and I have overdone it. And so it is easy to do. I mean, even if you don't think you're overdoing it, nobody has a perfect sort of forward ability magic crystal ball, and so it's easy to actually get to this state without intending to. And so one of the things that we found is sometimes the easiest way to do this is actually put services back together. Because I have too many, I have too much partial failure. Let me put them together and look for a way to simplify things. And so I wanted to highlight a few patterns of places that we can look for as opportunities to potentially recombine services. I do think you have to evaluate things on their own basis, but this at least gives you a set of things to look for where you can make a consideration. So the first one is if I have a service that has a single client, a single lonely client, then I would have to ask, should that service actually just be part of that client? Why do we have it out as a separate service if there's only one thing that uses it? And so that can be an opportunity to recombine things. Another one is if we have tight coupling, right? If every time I change service A, I have to make a change to service B, then that kind of suggests that I didn't draw the boundaries between those services in the right place. Right? And that maybe I ought to put these back together and look for a different way to divide that functionality. Similarly, correlated calls. If all of the clients who call service A immediately turn around and call service B, that also suggests that things might be more convenient if A and B were combined. And so I have an example that kind of pulls all of these things together. So in this case, the client application was actually a service. So it was an API facade layer, and so this is all running in our data center. And we had done a good job of really finally chopping up some of our services. So we had a service that knew about movies, one that knew about TV series, one that knew about on-demand videos, and one that knew about listings. So listings are the things that say, this show is on channel 10 at 8 o'clock, right? And what we found is for most of the time when that client service was processing a request, it had to talk to all of these services all of the time. And so this led us to things like, well, what do I do if I don't hear back from the on-demand service, right? Or what do I do if I don't hear back from all of these services? And so one of the things that we were able to sort of think about was we were able to actually modify this and migrate this over several steps to something that worked a little better. So the first thing that we did was all of these services, which are, by the way, are really good examples of, every object is its own service, right? This is sort of like the object-oriented CRUD model taken to the extreme, right? And so, but they all had notification interfaces. So every time there was a change, there was actually a place where you could listen to the changes. So we actually inverted what was going on here. So rather than having the client actually call these services, we changed things around and we had a single event processor that would actually listen to notifications for all of these and then publish a stream of updates back to the client. Because as it turned out, the total set of data that was involved here was actually relatively small. And it was small enough that each client, instance of the client, could keep a copy of the data. And then we wrote a distributed system library so that when we got a mirror of the data at one client, that could actually be mirrored to the other clients as well, so that all of the instances of this service were able to have a copy of this data. And so this actually this actually combines everything that I've talked about so far. So as it turns out, the sort of update interface was an idempotent interface. That was the way that we modeled it. And so retries were something that we were able to handle very well. We made it so that when a request came into one of these client services, it didn't have to talk to something else, right, in order to satisfy that request, because it already had a copy of the data. So one way of looking at that is we sort of smushed those services together in some sense. But then this also introduces sort of the asynchronous synchronous concept as well, because the idea is that updates to these things didn't actually happen that often. I mean, Hollywood only produces so many movies per year, and certainly not hundreds of thousands every second. And so, and even if a new movie is planned, it doesn't necessarily mean that you can see it on TV immediately, right? So this was a place where we were able to take advantage of this. And so even if that whole bottom part went away, it was okay if these mirrors got stale for a little while. Because this was completely hidden from the users, right? So we were able to decouple the process of updating these information from the rest of the application. If you're interested in the distributed system library that I mentioned, we actually open sourced it, and it's available on our GitHub page. But that's an entirely different talk there. So anyway, these are some of the patterns that we have pursued in order to try to make sense and live in this services-oriented environment. And so, you know, in my experience, 3 really good strategies for dealing with partial failure are defining idempotent service interfaces wherever you can. This gives you that great sort of resolving the semantic ambiguity and letting you retry things. Where you can't, try to think about dividing services by their criticality. So we sometimes think about dividing them according to functionality or sort of a step in an algorithm, which is a slightly different sort of way of looking at things. But that's the thing that gives you graceful degradation, right? So that when a partial failure happens, you can choose to ignore it in some cases. And then finally, if partial failure is a problem, try to subject yourself to it less, which is to look for opportunities to put services back together. And you know, I highlighted a few patterns or things where you can recognize and maybe identify an opportunity to put things back together. So thank you.